part 2 of the previous video was 7b59, and it's line 22 and the last three numbers are 7b59, and you want to go to 7b58 to read the first part of this particular type of video. Separatrix accelerating structures part 2, 5G Wow Seti. There's the alien radio signal. I'm getting frustrated because my nose keeps running today. Oscillations, transverse electron, wave modes, keyword research to be filmed. Wow, data. I guess I got allergies or something. May 18, 2013. Today's June 22nd. So we're talking about separatrix splitting in several videos. The last two, of course, the last one was 7b58, separatrix accelerating structures part 1. Quotes from the blog: accelerating structure continues. Nothing like repeating yourself, right? Okay. Let's just get rid of this. And I already did that. Goes to the blog. Okay. There are two main types of oscillations, the TE and the little MN, or the transverse electric modes where there is no longitudinal E field, and the TM and then MN, or transverse magnetic modes, which has no longitudinal B field. In addition, there are also TEM modes with purely transverse fields. The subscript MN indicates the order of a mode, with higher order modes requiring larger resonant cavities. Clearly, for the purposes of acceleration, a longitudinal E field is required to accelerate the beam along the beam pipe, such as only TM modes are used within the structure. The RF is injected into the structure at the front and extracted at the rear, hence the doubling of the number of waveguide couplers seen in figure 2.15. Okay, so the rate of advance of the E field maxima, the phase velocity Vp, is set by the spacing of the cavities within the structure, should be the same as the particle velocity. As such, a traveling wave structure is constructed from a number of approximately identical disks, whose widths govern the E field phase velocity. This gives it a similar appearance to that of the standing wave structure. In general, traveling wave structures are cheaper to produce for a particular gradient. However, it is possible to achieve higher gradients with a standing wave structure. Traveling wave structures are necessarily longer, since it is desirable to use up all the injected RF as it is dissipated along the length of the structure before being extracted. A standing wave structure has no such condition, since all the power is retained within the structure. As such, the shorter standing wave structures can hold a higher gradient. In addition, any breakdown within the cavity will result in a higher power deposition in a traveling wave structure, since the longer structure holds more power. However, both cavity types are required to achieve a higher gradient than is actually needed. This is a result of a phenomenon called beam loading. Beam loading results from the interaction of the beam with the conductive walls of the accelerating structure. As the beam passes through the cavity, the EM field surrounding the beam interacts with the cavity, producing a wake field that acts against the accelerating field. This reduces the magnitude of the longitudinal E field and hence the accelerating gradient. This is similar to the back EMF produced by an electric motor as a result of its inductance. This gradient reduction occurs gradually along the length of the bunch train, resulting in a smaller gradient for the rear bunches. To compensate for this effect, the RF input power at the NLC is ramped, so that the power reduction that occurs as a result of beam loading matches the power increase supplied by the RF system. As a result, the NLC accelerating structures are required to achieve an unloading gradient of 70 mVm, but a loaded gradient of 55 mVm. Since the size of the cavities in all dimensions is dependent upon the RF frequency, higher frequency RF drive is variable as it provides both a higher gradient and shorter bunches. For a smaller, cheaper structure, however, higher frequency RF is more difficult and more expensive to produce, with corresponding tighter tolerances required in the manufacture of the structures, further increasing the cost. There is therefore a trade-off in achieving the cheapest and most beneficial solution. The NLC main lineup uses an X-band drive frequency of 11.424 GHz with copper traveling wave structures, and that's from www-pnpphysics.ox.ac.uk. And we're still working on separatrix splitting. Thanks for watching.